In this lesson, we're going to learn more about functions. We'll look at tables, graphs, and equations of functions. We'll learn about function notation, and we'll also learn how to find the zeros of functions. To start, if you were to graph this equation, you would get a straight line that would look like this. In Chapter 2.2, we learned that you could use the vertical line test to determine if a graph is a function. If you use the vertical line test, any vertical line that you draw through this graph will only intersect the graph in one point. So this graph is a function. And if you'd like more of an introduction to functions, please watch my Chapter 2.2 video. So this equation represents a function. If you have an equation that represents a function, mathematicians like to label that equation using function notation. To do that, we replace y with f of x. F of x means the exact same thing as y. But what's nice about f of x is when you see an equation with f of x, you know right away that it's a function because we only use function notation with equations that are functions. So if you're asked to find f of 3, we know that f of 3 is y. So we could rephrase the question as find y. But this notation doesn't mean any y. This means a specific y. What's inside the parentheses, that represents x. So this notation means y when x is equal to 3. To find f of -5/7, we could again rephrase this as find y, but again, we're not being asked to find any y here. We're being asked to find y when x is -5/7. So here we have a table, and we know that this table represents a function because we see this function notation right here. We're using f of x instead of y. So for the first problem, we're asked, what is f of -5? Let's rephrase this question. Remember, this notation means y, so the question is asking, what is y? But this function notation is asking for a specific y. Remember, what's inside the parentheses represents your x value. So this function notation is asking, what is y when x equals -5? To answer that question, let's look at our table and let's find when x is -5. Here, x is -5. The corresponding y value is 1. So f of -5, or in other words, the y value when x is -5 is 1. The next question asks, for what values of x is f of x equal to 2? How can we rephrase this question? Remember that f of x just means y. So a different way to ask this question is, for what values of x is y equal to 2? Let's look at our tables and let's find when is y equal to 2, right here. And we want to know what is the corresponding x value. That would be -1. Next, we're asked to find the coordinates of the x-intercept. In our Chapter 1.6 video, we learned that all x-intercepts have something in common. Every x-intercept occurs when y equals 0. In other words, when f of x is equal to 0. So let's look on our graph and let's find when is y, or in other words, when is f of x equal to 0. That's right here. So to write the x-intercept as an ordered pair, our x-coordinate is -8, and the y-coordinate of our x-intercept is always 0. Last, we're asked to find the y-intercept. All y-intercepts have something in common. Every y-intercept occurs when x equals 0. So let's look at our table and find when is x 0, right here. So we can write our y-intercept as an ordered pair. The x-coordinate of every y-intercept is always 0, and the y-coordinate of our y-intercept is 3. Next, we're given a graph, and this graph is a function because it would pass the vertical line test. Any vertical line drawn through the graph would intersect the graph in only one point. So this is a function, and we're asked to find some information about this graph. First, we're asked to find the domain of this graph. In my chapter 2.1 video, we practiced finding the domain and range of graphs like these. To find the domain, we're wondering, what are all of the x values on our graph? Now, there are infinitely many points along this graph. So that means there are infinitely many x values in our domain. Interval notation is a nice way to describe the domain when you have infinitely many x values. For interval notation, we just list the lowest x value on our graph, then we put a comma, and then we list the highest x value on our graph. Now, the x-axis runs from left to right. So when we're looking for the lowest x value on our graph, we want the point that's furthest left on our graph, because as the x-axis goes towards the left, the x values get more and more negative. Let's pick a few points as our graph moves to the left, and we'll look at the corresponding x values. The x value of this point looks like it's -1. The x value of this point looks like it's -2. The x value of this point is -3. The x value of this point is -4. The x value of this point is -5. And as this graph keeps extending to the left, our x values will keep getting more and more negative. So when you're asked for the domain, if your graph extends infinitely to the left, that means your lowest x value will be -infinity. And for interval notation next to -infinity, we always use parentheses. And then we'll list a comma, and then we'll list the highest x value on our graph. Remember, as you move to the right, the x values get higher and higher and higher. So to find the highest x value, we want to find the rightmost point on our graph. Let's again just look at a couple points as we move in the rightward direction. The x value of this point is 1. This x value of this point is 2. The x value of this point is 3. The x value of this point is 4. The x value of this point is 5. So as our graph moves to the right, the x values are going to keep getting bigger and bigger. And this arrow indicates that our graph moves indefinitely to the right, so our highest x value will be +infinity. This problem specifies that we use interval notation to describe the domain, but just for extra practice, let's also write our answer in set builder notation. For set builder notation, we start with this general outline. We insert an inequality right here, which says that our x values go between negative to +infinity. Instead of writing this inequality, we could also use words in our set builder notation and replace this inequality with the words x is any real number. Next, we're asked to determine the range. Again, the range refers to the y values, and for interval notation, we write the lowest y value, then we put a comma, and then we put the highest y value. Since the y-axis runs up and down, our lowest y value will be the point furthest down on our graph, and the highest y value will be the point furthest up on our graph. Let's start with the lowest y value on our graph. Let's pick a few points as our graph moves downward, and we'll look at the corresponding y values. The y value of this point is -2. The y value of this point is -4. The y value of this point is -6. And if we keep going down, the y values will keep getting more and more negative. So since these arrows indicate that our graph goes down indefinitely, our lowest y value will be -infinity. Next, we need to find the highest y value on our graph. It looks like right here, our graph is the highest. There's no points higher than right here. So what is the corresponding y value of these points? It looks like the corresponding y value is 2. So the highest y value on our graph is 2. Remember, with interval notation, we always use parentheses next to positive or negative infinity. Since 2 is an actual y value on our graph, you want to use brackets so that we're including that point. So that's interval notation. Again, for extra practice, let's also write our answer in set builder notation. So for set builder notation, we'll start with this general outline, and then we want to insert an inequality here to describe the y values of our graph. We see that our y values range from -infinity to 2. So an inequality that we could use to describe that would be that all of the y values are less than or equal to 2. Next, we're asked to identify the x-intercepts. The x-intercepts are where your graph crosses or touches the x-axis, which would be right here on our graph. So that would be the order pairs -2, 0, and 2, 0. Next, we're asked to identify the y-intercept on our graph. The y-intercept is where the graph crosses the y-axis, which would be right here. And to write this as an ordered pair, the x-coordinate is 0, and the y-coordinate of that y-intercept is 2. What can often lead to confusion is the fact that the notation for interval notation is very similar to the notation for ordered pairs. For interval notation, we always list the lowest value, and then we put a comma and list the highest value. And for interval notation, we use parentheses if we do not want to include that endpoint, and we use brackets if we do want to include the endpoint. For ordered pairs, we always use parentheses, and then we list the x value on the right and the corresponding y value on the left. If you just saw something like this with no context, you wouldn't know if this was interval notation or if it was an ordered pair. But usually we'll be given the context, so we'll know if this is interval notation or we'll be told if this is an ordered pair. Okay, next we're asked if g of 3 is equal to -2, we want to write the ordered pair that corresponds to this information. Remember that g of 3 means y. So we could rewrite this statement as y equals -2, but remember, this means a specific y. This means y when x equals 3. So we know that y equals -2, so in our ordered pair, we put -2 in the y position. And we know that what's inside parentheses here represents the x, so we put a 3 in our x position of our ordered pair. Next, we're given this ordered pair, and we're asked to use this information to complete this function notation. For the ordered pair, -5 is our x, and we know that we always put the x value inside the parentheses, and -6 is our y, and we know that this notation means y, so we want to say y equals -6. What's nice about ordered pairs and function notation is that the order of the numbers stays the same. So notice we have a 3 first in the function notation and a 3 first in our ordered pair, and then we have a -2 second and a -2 second in our ordered pair. Same thing here, we write the -5 first and then the -6 second. Next, we're given a graph that represents a situation, and we're asked to find some information from the graph. We're told that this graph represents a young boy swinging on a swing. The x-axis represents the time, and the y-axis represents the height. So you can picture a boy swinging on a swing. He'll swing up and then down and then up and then down as time passes. This function is labeled function h. And first we're asked to find h of 5. How could we rephrase this statement? Remember, this means y, so we're being asked to find y, but we're looking for a specific y. We're looking for y when x equals 5. So let's look at our graph. Here's our x-axis, and when x equals 5, the corresponding y value is 0. So we can say h of 5, or in other words, the y value when x is 5, is 0. Next, we're going to get more practice finding the domain and the range. To find the domain of this graph, we're looking for the x values. And to write our answer in interval notation, we first list the lowest x value, then we put a comma, and then we list the highest x value. Again, the x-axis runs from left to right, so your lowest x value will be your point furthest left on the graph, and your highest x value will be the point furthest right on the graph. Sometimes it helps to use paper blockers like these, and when we're looking for the domain, we want to block the graph from the left and block the graph on the right. So our whole graph falls between these two paper blockers. Now we can easily see that our lowest x value, or the x value furthest left, is right here, and that x value is 0. So for our domain, we'll put a 0 here, and we want to include that, so we use a bracket. And then the highest x value will be the point furthest right on our graph, which is right here, and the corresponding x value is 15. So for our domain, we'll put a 15, and then again, we'll use a bracket to include it. Next, let's do the range. The range refers to the y values. Remember, the y-axis runs up and down, so to find the lowest y value, you look for the lowest point on your graph, or the point furthest down, and to find the highest y value, you look for the highest point on your graph. Let's again use these paper blockers, and when you're looking for the range, you want to block your graph from the bottom and the top, so our whole graph fits in this window. Now we can clearly see that our lowest points on the graph are right here, and these lowest points have a y value of 0. So for our range, we'll start with a 0 as our lowest y value. Then we look for the highest point or points on our graph, and these are the highest points on our graph. There's no points above here. So the y value of these highest points is 8. So this means that the x values are all between 0 and 15, and this means that the y values are all between 0 and 8. Next, we're asked for what values of t does h of t equal 8? For this problem, t is our x-axis and h is our y-axis. So how could we restate this question? Remember, our x-axis is t for time, so I just replace the t with an x. And then this notation means y, so I replaced this with y. So we're asking for what values of x does y equal 8? Let's find on our graph, when is y 8? Well, here's 8 on the y-axis, so it looks like y is 8 at this point, and at this point. And the corresponding x value of those points are 2.5. This point isn't labeled, but it's perfectly halfway in between 5 and 10, so that x value would be 7.5, and the x value of this point would be 12.5. Next, we're given this function, and we want to know, does this point lie on the graph of this function? So to start, I've just rewritten this function, but I've color-coded it. I put the y in blue and the x in red. We're given this ordered pair, which I've color-coded the x value in red and the y value in blue. To determine if this ordered pair lies on the graph of this function, we just want to plug in 4 for x and -2 for y and see if we get a true statement. So I've done just that. I've plugged in -2 for y and I've plugged in 4 for x. And I'm going to add a question mark here because we don't know if this is equal. We don't know if we'll get a true statement. We'll bring down the -2. -5/2 times 4 will give us a -10. And then we'll bring down the +8. And again, we'll bring down the -2. And -10 plus 8 will give us a -2. So we get a true statement. So does this point lie on the graph of the function? Yes. If we had gotten a false statement here, then our answer would have been no. For part B, we're asked, if x equals 6, what is f of x? Again, I started by copying down the exact given function. We're asked, if x is 6, what is f of x? So to determine this, we just want to plug in 6 for our x and find the corresponding f of x value. So I've plugged in 6 for our x, and now we want to compute this. If you take -5/2 times 6, you'll get -15. And -15 plus 8 gives us a -7. So when we plug in 6 for x, f of x is -7. For the second part, we're asked to write the corresponding point on the graph. So we'll write this as an ordered pair. We know that the x value of our ordered pair is 6 because we're told that. And we found y, or f of x, is -7. For part C, we're asked, if f of x is equal to 3, what is x? Again, to start, I've copied down the original given function, just color-coded it. We're told that f of x equals 3, so let's replace f of x with 3. And then we're supposed to find x. So after we plug in 3 for f of x, let's now solve for x. We'll start by subtracting 8. That will leave us with -5 is equal to -5/2 x. Next, to isolate x, you have two options. You can divide both sides by -5/2. The only downside of dividing by -5/2 is that sometimes it's difficult to correctly type that into your calculator, and also sometimes it's a pain to divide by a fraction by hand. So instead of dividing by -5/2, another way to isolate x is to multiply by the reciprocal. The reciprocal means you just flip this, which would give us -2/5. And if we multiply this side by -2/5, we also have to multiply the other side by -2/5. -2/5 times -5 will give us a +2. And when you multiply two reciprocals, you get 1. That's why multiplying by the reciprocal helped us to isolate x, because multiplying two reciprocals gives us 1, so we're just left with 1x, or in other words, x. So when f of x is equal to 3, our corresponding x value is 2. Lastly, we want to write the corresponding ordered pair. We found that our x value was 2, and the y value was given when we were told that f of x, in other words, y, is equal to 3. Last, we're going to talk about how to find the zeros of a function. We'll start with the definition. The zeros of a function are the values of x that make f of x equal to 0. We're going to start by finding the zeros of a graph. How do we find the zeros of a graph? Well, the zeros of a function are the values of x that make y equal to 0. Let's remember, what do we call those points on the graph when y is 0? We call those points the x-intercepts. For all x-intercepts, the y-coordinate is always 0. So to find the zeros of a function from a graph, we just need to find the x-intercepts. We're supposed to find the zeros of this function. Our x-intercepts are here and here. And again, the zeros are just the x-intercepts. The only difference between zeros and x-intercepts is that we often write x-intercepts as ordered pairs, but we never write zeros as ordered pairs. Zeros refer only to the values of x. So for zeros, we only write the x values of our x-intercept. So the zeros are the x value of this x-intercept, which is -2, and the x value of this x-intercept, which is +2. These are the x values where y, or in other words f of x, is 0. Next, let's find the zeros of this graph. Again, the zeros just mean the x-intercepts. So the zeros of this graph are here, here, and here. But remember, for zeros, we're only looking for the x value of your x-intercept. So the 0, or the x value of this x-intercept, is -2. The 0, or the x value of this x-intercept, is 1. And the 0, or in other words, the x value of this x-intercept, is 4. Next, how do we find the zeros of a function from an equation? Well, we know that the zeros are the values of x that make f of x equal to 0. So to find the 0 from an equation, we're going to plug in 0 for f of x and then solve for x. So let's actually start with part B. We want to find the 0 of this function. So I started by copying down the given function. So to find the 0 of a function from its equation, we plug in 0 for f of x. So in this case, we have j of x instead of f of x. So let's plug in 0 for j of x, and then we can proceed to solve for x. Because remember, the 0 is the x value that makes j of x equal to 0. So let's start by adding 9. That will leave us with 9 is equal to 4x, and then let's divide by 4, and that will leave us with x is equal to 9/4. So our 0 is 9/4. In other words, 9/4 is the value of x that made j of x equal to 0. Let's try this last problem. We're asked, is 2 a 0 of the function? Remember, a 0 is the value of x that makes f of x equal to 0. So another way to ask this question is, does x equal 2? Because remember, if 2 is a 0, that means 2 is your x value. So if we want to know if 2 is a 0, we want to know, does the x value 2 make j of x equal to 0? So I've started by copying down the original given function. Let's plug in 2 for x and see if it gives us 0 for j of x. So we plug 2 in for x. If we simplify, this would give us 8 minus 9, and 8 minus 9 simplifies to a -1. So plugging in 2 for x makes j of x -1. It does not make j of x equal to 0. So that means that 2 is not a 0. Because when you plug in 2 for x, you do not get 0 for j of x.